Most highly reflective metals, like the silver on the left, appear completely colorless, but the gold on the right has a vivid, distinct yellow hue. Or consider your screen. High-end smartphone displays produce perfectly deep, self-illuminated colors that somehow glow for thousands of hours without burning out. And if we push to the very edge of modern engineering, we find sprawling, supercooled structures like this, built to house quantum hardware. At a glance, precious metals, consumer electronics, and next-generation computers do not seem to share much. Try explaining how they work using classical physics or standard chemistry, and you will hit a wall. Those frameworks are completely insufficient here. To actually understand how these things operate, we have to look deep inside the heaviest atoms on the periodic table. There, we find a single quantum interaction that bridges the gap between the theory of relativity and the physical materials we use every day, a phenomenon known as spin-orbit coupling. To understand spin-orbit coupling, we start with an electron inside an atom. It has two distinct properties. First, it moves around the nucleus, giving it orbital angular momentum. Second, it has an intrinsic property called spin, acting like a tiny magnetic compass needle. In a classical laboratory view of the atom, things look pretty straightforward. You have a massive, stationary nucleus with a positive charge and a tiny negatively charged electron buzzing around it. But let's switch our perspective. Riding along with the electron is stationary. Instead, that massive, positively charged nucleus appears to whip around us. According to relativity, this apparent motion generates an effective magnetic field right where the electron sits. Now, remember that intrinsic spin? That tiny internal compass needle interacts directly with this newly generated magnetic field. Relativity dictates that the electron's physical motion through space and its internal magnetic orientation cannot operate independently. They are forced to physically interact. This equation shows the mathematical reality of that interaction. The total coupling energy depends heavily on the dot product of two specific vectors, the orbital angular momentum, L, and the spin angular momentum, S. The crucial factor is the exact angle between them. Physically, this means an electron's energy actually shifts depending on its orientation. If its internal spin points in the same direction as its orbital motion, the system has a slightly different energy than if those two properties point in opposite directions. This creates what physicists call fine structure.
A single electron state, which we would normally expect to have one exact energy level, cleanly splits into multiple, slightly separated levels based purely on how that spin aligns with the orbit. If you look at relatively light elements, like carbon or oxygen, the nuclei are small. The electrons move relatively slowly, the magnetic effect is incredibly weak, and the splitting is barely noticeable. But heavy atoms, like gold or lead, have massive nuclei with huge positive charges. To avoid falling into that massive nucleus, the inner electrons are forced to move at incredible relativistic speeds. This blistering speed drastically magnifies the effective magnetic field, blowing that energy split wide open. These massive nuclei force a relativistic environment onto their electrons, causing the energy levels to diverge into the distinct patterns we observe in heavy materials. Which brings us right back to our solid gold. Because gold is incredibly dense, its massive atoms create a severe relativistic spin-orbit split. This shifts its internal energy levels just enough to change how the metal interacts with incoming visible light. Instead of reflecting all visible wavelengths equally like silver does, gold's shifted quantum gaps cause it to absorb blue light, leaving the red and yellow light to bounce back into our eyes. We can also engineer this quantum splitting to build better screens. In standard fluorescent materials, electrons try to jump between different spin states to release photons, but quantum mechanics usually labels these specific transitions as forbidden, making them highly inefficient. To bypass this, engineers inject heavy metals like iridium into the organic compounds of OLED displays. The heavy nucleus creates massive spin-orbit coupling, which forces those forbidden spin states to mix. The result is a highly efficient, sustained glow called phosphorescence. We see this logic pushed further in spintronics, where the electron's magnetic spin is used alongside its charge to process information. Spin-orbit coupling provides the bridge between these properties,
enabling us to flip magnetic directions using standard electric current. This phenomenon, where an electron's spin is inextricably locked to its direction of motion, is the exact mechanism powering research into new topological insulators and advanced memory components for quantum computers. Spin-orbit coupling proves that the universe does not keep its physical laws in separate boxes. By understanding how relativity warps the quantum rules inside a single atom, we can explain the natural colors of our world and actively engineer the next generation of computing.